Right now, at this very moment, there is a chance, a genuinely good chance, that you are carrying titanium inside your body. Not in your pocket, not in your bag, inside your actual flesh and bone. Maybe it's a dental implant threaded into your jaw. Maybe it's a small pin holding a bone that shattered years ago in a fall or a crash. You have probably never thought about what that metal is, where it came from, or how impossibly long humanity had to struggle before it could even produce a single gram of it in a pure form. Because here is the thing that almost nobody knows, the thing that scientists and engineers had to live with for over 150 years. Titanium is one of the most abundant metals on this planet. It makes up nearly 1% of the entire Earth's crust. It is everywhere beneath your feet, locked into beaches, riverbeds, and mountainsides on every continent. And yet, and this is the part that should stop you cold, not a single human being held a piece of truly pure titanium in their hands until the 1930s. Not one. Not a king, not a general, not the most brilliant chemist alive. For 150 years, this metal existed in theory, in dirty fragments, in broken promises, and in the shattered dreams of some of the greatest scientific minds in history. Kilogram for kilogram, in the middle of the 20th century, titanium cost more than silver. More than silver. A metal that is, statistically speaking, buried almost everywhere you look. How is that possible? What kind of curse keeps a substance that common so completely out of reach? That is the question this story is going to answer. But to answer it fully, you need to understand that this is not just a chemistry story. This is a story about obsession, about the particular madness that grips a person when they know something extraordinary exists and they simply cannot get to it. It is a story about a quiet English clergyman walking along a river with mud on his boots, about a Berlin chemist who reached for the most ancient mythology he knew to name something he barely understood, about a Luxembourg engineer who crossed an ocean with nothing but a stubborn idea, and about the moment, one specific, silent, almost holy moment in a laboratory when the oldest prisoner in the history of science finally broke free. And it is, in the end, about you. About the world you live in, the planes you fly in, the hospitals that fix your body, and the walls of the room you are sitting in right now. Because titanium is not just a metal, it is the skeleton of the modern world, and almost nobody knows it. So let's go back. All the way back to where it started, to a beach in the English countryside, to a man who had no idea he was standing at the beginning of one of the longest, strangest journeys in the history of human discovery. The year is 1791. The place is a small, quiet corner of Cornwall, England, a county of rocky coasts, fishing villages, and the kind of damp, gray skies that make the occasional burst of sunlight feel like a gift from above. The man walking along the bank of the River Helford is not a famous scientist. He does not work in a grand university laboratory or lecture to hundreds of students. He is a pastor. His name is William Gregor, and he is 28 years old, with ink-stained fingers and a habit of carrying small glass vials in his coat pockets everywhere he goes. Gregor is what the 18th century would have called a natural philosopher, a gentleman who studies the world around him out of sheer, irrepressible curiosity. He keeps meticulous notes. He sketches minerals on the margins of his sermons. He is, by all accounts, a mild-mannered, deeply religious man who finds evidence of God's artistry in the composition of rocks and the color of river sediment. And on this particular autumn morning, he sees something that makes him stop walking. It is sand, but not ordinary sand. This sand is black, or very nearly so, a dark metallic shimmer running through the gravel at the edge of the stream, as if someone has ground up a piece of night sky and scattered it along the riverbed. Gregor kneels down and picks up a handful. He rolls it between his fingers. It is heavy for sand, unusually heavy. He reaches into his coat pocket and pulls out a small horseshoe magnet, because of course he has a horseshoe magnet in his coat pocket. He is William Gregor, and he holds it near the sand in his palm. And the sand moves. The grains pull toward the magnet with a definite, undeniable attraction. Gregor stares at his palm for a long moment. Then he takes out a vial and fills it with the black sand. Then he takes out another vial and fills that one too. Then he goes home. What follows over the next several months is one of the most quietly extraordinary scenes in the history of chemistry. In the back room of a country parsonage, surrounded by scripture and sermons and the smell of candle wax and coal smoke, William Gregor sets up a makeshift laboratory on what was probably a dining table. He dissolves the black sand in acids, fraction by fraction, separating out what he knows, iron mostly, which explains the magnetic pull, from what he does not recognize. And there is something he does not recognize. After the iron is accounted for, there is still a substance left, a whitish powder, something that does not match any mineral he has in his reference books, something that should not be there. Gregor is precise in his notes, careful and honest in a way that you have to admire. He does not claim more than he knows. He writes that he has found what appears to be a new metallic earth, a new elemental substance, but he cannot identify it, and he is not certain of its nature. He names the mineral he found it in after the local valley, Menachan. He calls his new discovery Menachanite. And then, this is the part that is almost painful to read, he publishes his findings in a small regional journal. Not a grand London scientific publication, not the Transactions of the Royal Society, a regional Cornish journal in German translation, which was not widely read, and which most of the scientific establishment of Europe never saw. For a few years, Menachanite sits in the margins of history, almost invisible. The man who first isolated one of the most important elements on Earth gets, in return, near total silence. A brief acknowledgement from a few colleagues, then nothing. The black sand in his vials just waits. This is the first great tragedy of titanium. It was found by a man too humble to shout about it, in a place too obscure for anyone to hear, and it almost vanished entirely. Because here is the cold, unsentimental truth about how science actually works. Discoveries do not survive on their own. They need champions, they need publicists, they need the luck of being in the right room at the right time. William Gregor was none of those things. He was a country parson who loved rocks, and so the element slipped back into the dark, like a secret the Earth was not yet ready to give up. But secrets have a way of surfacing again. Because in Berlin, at almost exactly the same moment, a very different kind of man was doing very similar work, and he had the voice, the platform, and the ambition that Gregor entirely lacked. The next chapter of Titanium's story was about to begin, thousands of miles away, in a city full of ambition and gas lamps, and the particular electric energy of a science on the edge of reinventing the world. Berlin, 1791. The city is young and hungry, a capital asserting itself on the European stage, a center of Enlightenment thought where salons crackle with debate, where chemistry and philosophy sit at the same dinner table, where the question of what the world is made of feels almost urgently political. Into this world steps Martin Heinrich Klaproth, and if William Gregor was the gentle, self-effacing discoverer, Klaproth is his polar opposite. Klaproth is 51 years old, heavy-set, methodical, and professionally formidable. He is already famous, already the man who, in 1789, identified a new element in pitchblende and named it uranium after the planet Uranus, which had only been discovered 8 years earlier. Klaproth has a gift for naming things. He thinks in grand terms. He sees chemistry not just as the analysis of substances, but as the gradual unveiling of creation itself. And he approaches that work with the gravity of someone who understands its importance. He is working with a sample of a Hungarian mineral, a dark, dense stone called red schorl, or what we now know as rutile. And after months of careful dissolution and precipitation and the painstaking labor of 18th century wet chemistry, he isolates an oxide, a metallic oxide, something he has never seen before. He does not yet know, cannot know, that a shy English clergyman has already been here, already held this substance, already wondered at it. Klaproth believes, with complete sincerity, that he is the first. And so he does what great discoverers do. He reaches for a name worthy of the thing he has found. He does not choose a name from geography or from a sponsor or from a Latin description of the mineral's color or weight. He reaches instead into the oldest stories he knows. He calls it titanium. He names it after the Titans. Think about that choice for a moment, because it is not accidental. Klaproth was deeply read in classical mythology, and the Titans occupied a specific, loaded place in the Greek imagination. They were not simply giants or monsters. They were the first children of the earth, the primordial powers born from Uranus, the sky, and Gaia, the earth itself. They ruled the cosmos before the Olympians, before Zeus and his family, before the gods of reason and civilization. The Titans were older, rawer, more elemental. They were associated not with wisdom or beauty or craft, but with brute force, with deep time, with the unrefined energy of creation. And crucially, they were defeated. They were overthrown by their own descendants and cast into Tartarus, the deepest pit beneath the earth, where they remained imprisoned for eternity, locked in the dark. When Klaproth named this metal titanium, he was making, perhaps without fully realizing it, a prophecy. Because this element, abundant, powerful, potentially extraordinary, was going to spend the next 150 years in exactly the condition of those ancient prisoners, trapped underground, known to exist, impossible to reach, maddening in its inaccessibility. The name was perfect. It was almost too perfect. And there is something else worth noting about this moment. When Klaproth eventually learned about Gregor's prior discovery, and to his great credit, he did seek out that information and acknowledge it, he publicly gave the Englishman full credit for the first isolation of the element. Klaproth was not a thief of discoveries. He was a man of integrity. But the name stuck. It was his name. And so the history of this element carries both men. Gregor, who found it first in the black sand of a Cornish stream, and Klaproth, who heard something mythological in its resistance and gave it a name that would echo through the centuries. Titanium. Say it out loud. Even the sound of it is different from other elements. Not the soft domesticity of carbon or the clinical precision of hydrogen. Titanium sounds like something that belongs in an epic, something that should be carved on a temple wall. And that sound, that sense of ancient scale, is exactly right, because the story of this element is, in every sense, an epic. An epic of struggle and failure and eventual hard-won triumph. But at this moment in history, the triumph is 150 years away. Right now, in the last decade of the 18th century, all humanity has is a name and a handful of dirty oxide powder, and the first faint awareness that somewhere in the earth, something extraordinary is waiting. The Titans were cast into the pit, and titanium, their namesake, was about to follow them, into a century of scientific darkness that would defeat the greatest chemists alive, one after another, like a challenge issued by the earth itself. A century. One full century of failure. Imagine that. You were a chemist in 1805, or 1840, or 1870, and you have read the papers, you have seen the analysis, that there is an element called titanium, that it is apparently abundant, that it appears to have remarkable properties when isolated. And you try. You apply everything you know. You use the best acids available, the strongest reducing agents, the most advanced equipment that your era can produce. And you fail. Not just you, everyone fails. The greatest names in chemistry of the 19th century lined up before this element and were turned away, one by one, as if titanium had a bouncer at the door and a permanent policy of exclusion. And here is why. Here is the secret that took science so long to understand, the reason the Titans stayed imprisoned for so long. Titanium has an extraordinary, almost pathological hunger for impurities, not a preference, a compulsion. At high temperatures, the metal will react with almost anything it touches: oxygen, nitrogen, hydrogen, carbon. Even trace amounts of these elements, amounts too small to measure accurately with 19th century instruments, are enough to completely destroy titanium's mechanical properties. You can have titanium that is 99.8% pure, and it will still be brittle. It will shatter like ceramic. It will not bend. It will not hammer. It will not do any of the things a useful metal needs to do. The impurity does not weaken it gradually, the way rust weakens iron over years. It corrupts it absolutely and instantly, at the molecular level, turning what should be a flexible, extraordinary metal into something that crumbles at a touch. And in the 19th century, with the laboratory technology available, producing truly pure titanium, pure enough to behave the way a metal should, was simply not possible. The instruments did not exist. The techniques did not exist. The understanding of contamination at that scale did not exist. So every chemist who tried to isolate titanium got something that looked like titanium, something that tested positive for titanium, but that behaved, when handled, like a cruel joke. The metal would form in the crucible, gray and promising, and then shatter the moment they tried to work it. Or it would be so brittle that it crumbled into dust under the lightest hammer blow. Over and over again, for decades. The frustration must have been almost unbearable, and you can feel it in the increasingly desperate language of the scientific papers from this period. Researchers began to write with a baffled, almost wounded tone, as if the element itself were mocking them. And then, in the 1890s, things got worse. Because into this vacuum of genuine progress stepped a new and particularly modern kind of actor, the fraudster. The story that filtered through the scientific community in 1893 and 1894 was almost too embarrassing to put in writing. A European supplier, the details remain murky, which is itself revealing, had been selling what was marketed as purified titanium metal, small ingots, silver gray, convincingly heavy, with all the right visual characteristics. Scientists in Germany, France, and England purchased this material. Some published papers based on experiments with it. And then someone, doing careful analysis, noticed something very wrong. The density was off. The spectroscopic signature was wrong. What was being sold as pure titanium was, in fact, aluminum, ordinary aluminum, which happens to be silver gray, that had been alloyed with small amounts of titanium and, in some cases, lightly surface treated to affect the right appearance. It was fraud. Deliberate, targeted fraud aimed at the scientific community's frustration with a material that everyone wanted and nobody could actually produce. The incident caused a minor scandal and accomplished something poisonous. It planted a seed of genuine doubt. Was pure, ductile, workable titanium even real? Or was the very idea of a useful titanium metal a kind of collective self-deception, a goal that chemists kept chasing because giving up felt like admitting defeat? By 1900, the scientific consensus on titanium could be summarized very simply. Yes, it exists as an element. Yes, it is abundant. No, we cannot make it into anything useful. We are not sure why, and we are starting to wonder if we ever will. It was the most maddening material on Earth. It sat in the crust of the planet in vast quantities, in black beaches in Australia and India, in river sands in Ukraine, in coastal dunes in Florida. And every attempt to coax it out of its mineral prison and into a form that humanity could use ended in the same way: failure. Expensive, time-consuming, humiliating failure. Titanium had become, in the laboratories of the Western world, something worse than a mystery. It had become a reputation, a byword for impossibility. Young chemists were quietly advised to stay away from it. The careers of brilliant men had been spent on it and come to nothing. The metal's mythological name felt less like a tribute and more like a warning. This is a titan. Do not attempt to chain it. You will be the one who ends up in the pit. And so the 20th century arrived, with titanium still locked in its stone, still inaccessible, still theoretically perfect and practically useless. And the world, for the most part, had simply moved on. Steam engines ran on steel. Aircraft, those fragile new aircraft, were built from wood and fabric, and later aluminum. Titanium was a curiosity, a footnote, an elemental embarrassment. Something that was supposed to be magnificent and kept turning out to be nothing at all. But there was one man. There is always one man. He was not famous. He was not at a great university. He was working in the early 1930s with very little money and a very great deal of stubbornness in a laboratory in Europe that was about to be consumed by the darkest chapter in the continent's history. He had been trying to solve the titanium problem for years. He had failed many times. He would fail many more times before he succeeded, but he would not stop. He could not stop, because the problem had gotten into him the way problems get into certain kinds of people. Not as a challenge to overcome, but as a truth to be excavated. He knew the metal was there. He knew it was extraordinary. He knew, with a certainty that was almost irrational, that there had to be a way. His name was Wilhelm Kroll, and he was about to change the history of the world, though neither he nor the world would fully understand that for another decade. But that story, the story of the man who finally broke the curse, that is the next chapter. And it begins not in triumph, but in flight. Wilhelm Kroll was not the kind of man history tends to celebrate. He was not charismatic. He did not give rousing speeches or write elegant prose or cultivate the kind of powerful friendships that open doors in academic institutions. He was, by most accounts, quiet, stubborn, meticulous, and almost pathologically unwilling to accept that a problem was unsolvable. He was born in Luxembourg in 1889, the same decade, incidentally, when the aluminum fraud scandal was embarrassing the European scientific community. And by the time he was 30, he had already decided that titanium was going to be his life's work. Not a chapter in his career, his life. That kind of decision, made by a young scientist in the early 20th century, should be understood for what it truly was, a form of madness. Or perhaps a form of faith. The line between the two, in science, is thinner than it appears. Through the 1920s, Kroll worked in Europe, experimenting, failing, refining, failing again. He understood the contamination problem better than almost anyone alive. He had spent years reading every paper ever published on titanium, and there were not many, because most serious chemists had abandoned the field. And he had come to a conclusion that was both obvious in retrospect and radical at the time. If titanium reacts with oxygen, nitrogen, and hydrogen in the air, then you must keep it away from the air. Completely. Not mostly. Completely. Every previous attempt to produce pure titanium had been done in open or semi-open apparatus, where trace contamination was inevitable. Kroll's insight was that you needed a closed, inert environment, a sealed system filled with a gas that would not react with the metal at all. An inert gas. Argon. At high temperatures, in the complete absence of oxygen and nitrogen, with no water vapor, no carbon dioxide, nothing reactive, maybe, just maybe, titanium would behave. But building that kind of apparatus in the 1920s and early 30s was extraordinarily difficult and very, very expensive. And Kroll had neither the money nor the institutional support to do it properly. He scraped funding, he begged equipment, he worked in conditions that would be considered entirely unacceptable today, with gases that could asphyxiate, with temperatures that could melt steel, with no safety infrastructure beyond his own careful attention and a deep, lived familiarity with what his equipment could and could not do. And then history intervened in the worst possible way. By the mid-1930s, Europe was changing in ways that made scientific research increasingly impossible for a man with Kroll's independent spirit and non-conformist habits of mind. The political atmosphere in Germany and across much of Central Europe was becoming claustrophobic, dangerous, hostile to the kind of patient, curiosity-driven work that Kroll valued. His funding dried up. His laboratory access was restricted. The project that had consumed 15 years of his life was being strangled by forces that had nothing to do with chemistry. And so, in 1936, Wilhelm Kroll made a decision that would change the history of materials science. He packed what he could, his notes, his designs, his irreplaceable accumulated understanding of the titanium problem, and he immigrated to the United States of America. He arrived in a country still clawing its way out of the Great Depression, a country where money was tight and industrial research was focused on practical, immediate problems. He was middle-aged, foreign, and working on a material that the American industrial establishment considered a hopeless curiosity. He found a small amount of support from the United States Bureau of Mines. Not generous support, not the kind of funding that builds great laboratories, but enough. Enough for a modest facility, enough for a small team, enough to try. The laboratory he worked in during the late 1930s was, by the standards of the era, unremarkable. Small rooms, basic equipment, the constant background noise of an institution that was doing many things at once and considered none of them particularly glamorous. But inside that space, Kroll was doing something that no one in the world had ever managed to do. He was building, piece by piece, the exact environment that titanium needed to become itself. The core of his process was elegant in principle, even if brutal in execution. Titanium in nature does not exist as a pure metal. It exists bound to oxygen, as titanium dioxide, locked into mineral compounds. To get the metal out, you first have to convert the dioxide into titanium tetrachloride, a liquid at room temperature, which can be purified by distillation to an extraordinary degree of cleanliness. Then, and this was Kroll's crucial innovation, the step that nobody else had thought to do quite this way, you react that pure titanium tetrachloride with molten magnesium metal inside a sealed steel retort under an atmosphere of pure argon. The magnesium strips the chlorine away from the titanium. It sacrifices itself, chemically speaking, so that the titanium can be free. And if everything is done correctly, if the argon atmosphere is truly pure, if the retort is truly sealed, if the temperature is controlled just right, what you get at the end is not a liquid, not a powder, not an alloy, but a sponge. A metallic sponge, porous, silver gray, crumbling at the edges like a strange mineral bread, but made of titanium. Pure titanium, ductile titanium, titanium that can be hammered, rolled, and worked without shattering. And on a day in 1938, the exact date is not recorded with the ceremony it deserves, Wilhelm Kroll opened his retort, reached inside with tongs, and held in his hands the thing that had defeated every chemist since 1791. He had done it. He had finally, after 147 years, broken the curse. By all accounts, he was not given to theatrics. He did not shout or weep or run into the street. He looked at the sponge for a long time. He made notes. He began preparing for the next run to verify that it was repeatable, because that is the kind of man he was. But the weight of the moment, had he allowed himself to feel it, must have been almost crushing. He was holding, in his hands, the answer to a question that had outlasted Napoleon, outlasted the American Civil War, outlasted the invention of the telephone and the automobile and the airplane. He was holding the key to a material that, in the years to come, would reshape aviation, reshape medicine, reshape the entire infrastructure of the modern world. He was holding it, and he was alone in a small government laboratory in a country that was not his own, and the world was less than a year away from a war that would change everything. The baby Titan had been born, but the world it was born into was about to catch fire. The war changed everything about titanium, not immediately, and not in the way you might expect. During the Second World War itself, titanium production was too small, too difficult, and too expensive to play any significant military role. The process Kroll had developed worked, but scaling it up from a laboratory operation to an industrial one was an enormous engineering challenge that would take years. What the war actually did was something more subtle and in some ways more consequential. It showed engineers and military planners exactly where the limits of existing materials were, and it made clear that those limits were going to matter enormously in the years ahead. By 1945, both the United States and the Soviet Union had seen enough of aviation technology to understand where things were heading. Jet engines were the future, that much was obvious. The Germans had them, the British had them, the Americans were building them, and jet engines meant speeds that propeller aircraft could not approach. And speeds, in aviation, are not just a matter of going faster, they are a matter of heat. When an aircraft moves through air at very high speed, the friction between the fuselage and the atmosphere generates heat. At moderate speeds, the speeds of propeller aircraft, this heat is manageable. But as you approach the speed of sound and then exceed it, and then begin pushing toward 2 and 3 times the speed of sound, the heat becomes catastrophic. Aluminum, the wonder material of the Second World War, the metal that had made modern aviation possible, starts to lose its structural integrity at sustained temperatures above about 150 degrees Celsius. At the speeds that military planners were now dreaming about, Mach 2, Mach 3, the far edge of the atmosphere, aluminum would simply not work. It would soften, it would deform. In extreme cases, it would melt. What was needed was a material that was light enough to fly with, strong enough to survive the speeds, and thermally stable enough not to fall apart when the atmosphere pushed back. Steel was strong and heat-resistant, but far too heavy. Aluminum was light, but insufficiently resistant to heat. And titanium, Kroll's titanium, the titanium that now existed, that could be produced in quantity if you were willing to spend the money. Titanium was both. It was roughly as strong as steel at a fraction of the weight. Its melting point was over 1,600 degrees Celsius. It would not corrode, it would not fatigue easily, it would not buckle under thermal stress. It was, in every relevant dimension, exactly what the new age of aviation needed. Both superpowers understood this simultaneously. And what followed was one of the most consequential, and least publicly documented, industrial competitions of the entire Cold War. The United States moved first, and it moved with characteristic American scale. In 1948, the Bureau of Mines, the same institution that had supported Kroll's lonely experiments a decade earlier, published the Kroll process openly, making the method available to American industry. Within a few years, titanium sponge production in the United States went from a few hundred kilograms per year to tens of thousands of tons. The military-industrial complex latched onto the material with an intensity that bordered on obsession. Early jet aircraft incorporated titanium components, then more components, then entire structural assemblies. The airframes were being redesigned around the material's properties rather than the other way around. But the Soviets were watching, and they were not idle. Here is where the story takes a turn that feels almost too dramatic to be true, except that it is entirely, documentably true. The Soviet Union in the 1950s faced a serious problem with titanium. They understood its importance. They had their own titanium-bearing mineral deposits, enormous ones in fact, in Ukraine and the Urals, among the largest in the world. But they were behind on the processing technology. The Kroll process required magnesium, and more critically, it required the industrial infrastructure to handle the material safely at scale. The sealed environments, the inert gas systems, the specialized equipment. Building all of that from scratch takes years. And years were something the Soviet military establishment did not feel it had. And so the Soviet government, and this is the part that makes intelligence historians laugh with a particular weary appreciation, set up a network of front companies in neutral countries and in the United States itself, through intermediaries and dummy corporations and carefully structured commercial transactions, to purchase American titanium technology, American titanium sponge, and, in some cases, American titanium processing equipment. The primary material that the Soviet Union used to build its most advanced military hardware in the 1950s and 60s, hardware explicitly designed to threaten the United States, was, to a significant degree, supplied by American industry, which had no idea what its customers were ultimately using it for. When American intelligence eventually pieced together what had happened, the response ranged from horror to black comedy. The Soviet Union had used the very openness of American industrial commerce against itself, and the titanium had flowed east, ton by ton, transformed into weapons. But the most visible symbol of titanium's military coming of age belongs not to that intelligence drama, but to something you can still see in museums today. The Lockheed SR-71 Blackbird. Even its name sounds like titanium feels. Dark, fast, slightly threatening. The SR-71 was conceived in the late 1950s as a strategic reconnaissance aircraft capable of flying at Mach 3.2, more than 3 times the speed of sound, at altitudes above 24 kilometers. At those speeds, the leading edges of the airframe reached temperatures of over 300 degrees Celsius. The entire aircraft was, in effect, a controlled thermal event. The only material that could survive those conditions at the required weight was titanium. 85% of the SR-71's airframe was titanium. Not some titanium, not titanium in the key structural members. 85% by weight of the entire aircraft. Building it required the United States to develop entirely new machining techniques, entirely new welding procedures, entirely new metallurgical understanding. The titanium was so reactive during machining that ordinary cutting tools would contaminate the metal at the cut surface, degrading its properties. Entire new categories of tooling had to be invented. The factory floor where the SR-71 was assembled had to be kept at carefully controlled humidity and temperature because even atmospheric moisture could affect the quality of titanium welds. Workers wore cotton gloves to avoid leaving fingerprints on titanium components because the salts in human sweat could cause micro-corrosion at the contact point. It was, in every sense, the most demanding manufacturing project the American aerospace industry had ever attempted. And it worked. The SR-71 flew for the first time in 1964, and it flew so fast that no weapon system ever successfully shot one down. When surface-to-air missiles were fired at it, the pilots simply accelerated. The aircraft outran its threats. It outran everything. It was titanium-made flight. Meanwhile, under the surface of the world's oceans, the Soviet Union was demonstrating its own mastery of the material in a very different theater. The Alpha-class submarine, known in Soviet service as Project 705, was one of the most remarkable military machines ever built. Its pressure hull was constructed almost entirely of titanium alloy. This made it extraordinarily expensive. Each vessel cost a sum that made Western naval architects wince, but it also made it unlike anything else in the water. Titanium's corrosion resistance meant the hull would not rust, even in salt water over decades of service. Its strength-to-weight ratio meant the hull could be made thinner than steel while still resisting the crushing pressure of deep water. The Alpha could dive to depths that exceeded the operational limits of most Western anti-submarine torpedoes. When pursued, it could reach speeds of over 41 knots submerged, faster than any torpedo in service at the time. Hunting an Alpha was, for Western navies, an exercise in humiliation. The thing that was supposed to be the hunter became the prey. And all of it, the speed, the depth, the invulnerability, was titanium. The Titans, Klaproth's ancient mythological prisoners, had finally escaped from the underground. They were flying through the stratosphere and racing through the deep ocean. They had been waiting 150 years for this, and now that they were loose, they were making up for the lost time with a furious, silver energy that the world had never seen before. But war, and the machinery of war, was only one side of this story. Because at the same moment that engineers were fitting titanium into missiles and aircraft and submarine hulls, a surgeon in Sweden was looking at something under a microscope that would send the metal in a completely opposite direction, toward healing rather than destruction, toward the inside of a human body, toward something that felt, after all the violence and secrecy of the Cold War years, almost like grace. The year is 1952. And a Swedish orthopedic surgeon named Per-Ingvar Brånemark is not thinking about Cold War espionage, or supersonic aircraft, or the geopolitics of titanium supply chains. He is a young researcher at the University of Gothenburg, and he is interested in a much smaller question. How does bone heal? Specifically, he wants to observe the process of bone healing at the cellular level, in a living organism, in real time. This is technically very difficult in 1952, because to observe living cells, you need to be able to see them, which means you need an optical instrument inside the body, which means you need to implant something into living tissue and leave it there for an extended period while the tissue remains functional around it. Brånemark designs a small titanium optical chamber, a tiny device that can be screwed into the bone of a laboratory rabbit's leg, with a window through which a microscope can be directed at the cellular activity inside. The titanium is chosen because it is light, strong, non-magnetic, and expected to be biologically inert. That is, the body should recognize it as a foreign object, wall it off with fibrous scar tissue, and essentially tolerate its presence without integrating with it. This is the expectation. This is what every medical textbook says about metals implanted in bone. The body rejects them, or at best, encapsulates them. When the experiment concludes, some months later, Brånemark's team begins the process of removing the titanium chambers from the rabbit's legs. And they encounter a problem. The chambers will not come out. Not because of mechanical failure, not because of corroded threads, but because the bone has grown into the titanium, around the titanium. Through the surface texture of the titanium, the tissue has not rejected the metal or walled it off. The tissue has adopted it. The cells behave as if the titanium is part of the body's own architecture, as if it is, in some fundamental biological sense, the same thing as bone. Brånemark stares at this result for a long time. Then he looks at it again. Then he begins, very carefully and methodically, trying to understand what has happened. What he eventually concludes, after years of further research, is that titanium has a property that no other common metal possesses to the same degree. When titanium is exposed to oxygen, even the trace amounts of oxygen in a biological environment, it forms an extremely thin, extremely stable layer of titanium dioxide on its surface. This oxide layer is chemically inert to the point of near invisibility to the immune system. It does not trigger the inflammatory responses that other metals provoke. It does not leach ions into surrounding tissue. It does not corrode in the presence of bodily fluids, and crucially, it has a surface texture, at the microscopic level, that encourages osteoblasts, the cells responsible for building bone, to attach to it and begin constructing new bone material directly against the implant surface. The body does not fight the titanium, the body builds on it. Brånemark names this phenomenon osseointegration, from the Latin words for bone and integration. And then he spends another decade carefully, almost obsessively testing it, because he understands that what he has found is potentially revolutionary, and revolutionary findings in medicine require airtight evidence before any responsible person will act on them. By the 1960s, he is ready to try it in a human patient. The first recipient of a titanium dental implant was a Swedish man named Gösta Larsson, who had a severe jaw defect that had left him without the bone structure necessary to support conventional dentures. In 1965, Brånemark implanted 4 titanium fixtures into Larsson's jaw. The bone grew around them. The implants integrated completely. Larsson lived with those implants for the rest of his life, over 40 years, without rejection, without complications, without pain. A foreign object, a piece of refined metal, had become functionally indistinguishable from his own skeleton. Think about what that means. The property that made titanium so maddeningly difficult to isolate, its extreme chemical reactivity, its refusal to remain pure in the presence of other substances, had been inverted inside the human body into something miraculous. Outside the body, titanium's hunger for oxygen created contamination problems that drove engineers to despair. Inside the body, that same hunger created a stable, invisible oxide layer that the immune system could not identify as a threat. The curse inside the living organism became a blessing. The metal that could not be touched without being corrupted by the outside world was, inside the body, incorruptible. Today, the implications of that discovery are visible in the lives of hundreds of millions of people. Over 500 million dental implants have been placed in human jaws worldwide. The hip replacement surgery that allows elderly people to walk without pain, the titanium femoral stem that slots into the bone of the upper leg and fuses with it over months, is performed over 1 million times per year in the United States alone. Spinal fusion surgery uses titanium rods and cages. Knee replacements use titanium components. The small plates and screws that hold shattered bones together while they heal, the hardware that gets placed in wrists and ankles and cheekbones after accidents, they are titanium. The cardiovascular stents that hold open clogged arteries, threaded through blood vessels on a catheter and expanded at the point of blockage, many of them are titanium alloy. The cochlear implants that give hearing to people born deaf use titanium housings. The skull plates that protect repaired brain injuries are titanium. Somewhere in the world, right now, a surgeon is holding a titanium instrument and implanting a titanium component and saving or restoring a life that without this metal would be diminished, compromised, or simply over. There is something that Brånemark said late in his life, after he had watched his discovery transform medicine across 6 decades, that seems worth pausing on. He talked about how the body receives titanium not as an intruder, but as a collaborator. How the boundary between the implant and the bone becomes, over time, essentially invisible, not just mechanically, but biologically, at the cellular level. The bone cells do not know they are growing against refined metal rather than natural tissue. They do not distinguish. They build. And the metal, which spent so long resisting every human attempt to master it, finally becomes still inside the body. It stops fighting. It allows itself to be incorporated. The Greek mythologists imagined the Titans as beings of pure, destructive force, elemental and untamable, imprisoned because they were too powerful to coexist with the order of the world. But inside a human body, the metal that carries their name does something the Titans themselves never managed. It makes peace. It becomes part of something larger than itself. It accepts its place in the structure and does its work without drama, without noise, without the constant violent resistance that defined its first 2 centuries. A titanium hip implant in the body of an 80-year-old woman makes no sound. It has no pulse. It feels, if she thinks about it, like nothing at all, which is exactly what it should feel like. Which is, in its quiet way, the most extraordinary thing about it. You have been told, at some point in your life, that titanium is an exotic material, something expensive and specialized. The metal of fighter jets and surgical implants, and the watches worn by people who want to signal that they are serious. This is understandable. This is the story that advertising is told, and advertising is very good at its job. But here is the truth, and it is one of the strangest facts about the modern world. Roughly 95% of all the titanium extracted from the Earth every year never becomes a structural metal at all. It never becomes a jet engine component, or a bicycle frame, or a surgical screw. It becomes a powder, a very specific, very fine, very brilliant white powder, titanium dioxide. And that powder is everywhere you look right now. The walls of the room you are in, if they are painted, and they almost certainly are, contain it. The paper this might be printed on contains it. Your toothpaste contains it. Your sunscreen contains it. If you have ever eaten a white candy coating, a white frosting, a white chewing gum, you have consumed it. The plastic casing of the device you might be listening on contains it. The white lines painted on roads contain it. The white brightness of your LED screen, the opacity of your shampoo, the whiteness of processed cheese, all of it, or very nearly all of it, owes its color to microscopic crystals of titanium dioxide, mined from beach sands on the other side of the world, and refined into the pigment that the modern world decided, sometime in the early 20th century, it could not live without. The history of white is older than you think. Before titanium dioxide, the dominant white pigment in the world was lead white, a compound of lead carbonate that had been used since ancient Egypt to paint walls and faces and pictures. Lead white was brilliant, opaque, durable, and also, as the 20th century came to understand with increasing alarm, profoundly toxic. The lead leached from old paint into household dust. Children who lived in houses with lead paint on the walls were ingesting it continuously, in microscopic quantities, with consequences for neurological development that the medical community spent most of the 20th century gradually uncovering and quantifying. By the 1920s, the search for a non-toxic alternative to lead white had become a genuine industrial priority. Titanium dioxide had been identified as a potential pigment as early as 1916. Its optical properties were extraordinary. The crystals scatter light with an efficiency that exceeds every other white pigment known to chemistry. A very small amount of titanium dioxide makes paint vastly more opaque than an equivalent amount of lead white or zinc white, the other main competitor. You need less of it to cover more surface. It is cheaper per unit of opacity. It is completely non-toxic. It does not yellow over time, as some organic pigments do. It is chemically stable in almost any environmental condition. It was, in every dimension that mattered to the paint industry, a perfect material. By the 1930s, titanium dioxide had displaced lead white as the dominant white pigment in industrial paints in the United States. By the 1950s, it had done so globally. Today, roughly 8 million tons of titanium dioxide are produced every year. Let that number settle for a moment. 8 million tons per year of a single compound derived from a single element. The sheer industrial scale of this production is almost impossible to visualize. Think of it this way. The entire annual production of pure titanium metal, all the jet engine blades and surgical implants and bicycle frames and spacecraft components in the world, amounts to roughly 300,000 tons per year. The titanium dioxide pigment industry is more than 25 times larger. The glamorous, high-technology metal that fills the pages of aerospace engineering journals is, by mass, a tiny sideline to the industry that makes your walls white. The supply chain for titanium dioxide begins, mostly, in places that look nothing like chemistry. The primary ore minerals, ilmenite and rutile, are found in heavy mineral sand deposits that occur along ancient coastlines. Australia, South Africa, Canada, India, Mozambique, Ukraine. These are the major producing regions, and the extraction process in many of them looks, from a distance, like ordinary beach mining. Huge dredges float on artificial ponds, scooping up the sand from beneath the surface. Separation plants use gravity, magnetism, and electrostatic charge to sort the heavy mineral grains from the ordinary quartz and feldspar that make up most beach sand. The rutile and ilmenite are concentrated, dried, loaded into containers, and shipped to processing facilities where the conversion to titanium dioxide pigment begins. But there is a shadow over this supply chain that most people who buy paint or toothpaste or sunscreen never think about. The conversion of ilmenite to titanium dioxide pigment produces significant quantities of acidic and radioactive waste. The ore minerals are often co-deposited with thorium and uranium compounds, which have to be separated and managed. The sulfate process, one of the two main industrial routes to titanium dioxide, generates large volumes of sulfuric acid waste. The chloride process is cleaner, but requires more energy and more capital. In several countries, the communities near titanium mineral sands operations have raised concerns about groundwater contamination, habitat disruption, and the long-term management of radioactive residue from ore processing. The story of titanium dioxide is, in this sense, a deeply modern story, a material that creates beauty and cleanliness and protection from ultraviolet radiation, produced by a process that generates problems that the industry is still working out how to manage. The whiteness of your walls comes at a cost that is paid, unevenly, by people in places you have probably never heard of. There is a particular irony here that feels almost literary. Titanium is the metal of purity, chemically inert, biologically invisible, brilliantly white. The word that people reach for when describing titanium products is always clean. Clean lines, clean aesthetics, clean performance. And yet the industry that delivers this cleanness to the world, that provides the white pigment in every painted surface, every printed page, every cosmetic product, is, at the industrial source, anything but clean. The dunes of Australia are moved, the rivers of Ukraine run cloudy, the mineral sands of South Africa are sorted under conditions that generate acid and dust and long-term land disturbance. The substance that humanity uses to signify purity requires, at its origin, exactly the kind of messy, complicated, environmentally consequential extraction that purity is supposed to transcend. This is not a reason to despair, it is a reason to pay attention. Because the global economy runs on materials whose origins most people do not see, and titanium dioxide is simply one of the clearest examples of a pattern that runs through almost everything the modern world consumes. Every surface that is white and bright and clean has a supply chain that is not. And the 8 million tons per year keep moving. From the beaches, to the factories, to the pigment plants, to the paint companies, to the hardware stores, to the walls of 1 billion homes. And most of the people looking at those walls have never once thought about the black sand on the other side of the world that made the whiteness possible. So here is a question to sit with. And it is not rhetorical. If the machine that produces global whiteness, the mining operations, the processing plants, the chemical factories, the shipping networks, were to slow down or stop, even for a few months, what would actually happen? How white is the world's dependency on this one compound? How brittle is the infrastructure of brightness? That question is not as abstract as it sounds, and in the chapters ahead, as we look at how tightly wound the global titanium supply chain really is, it will come back with an urgency that feels considerably less comfortable than paint. There is a galaxy called the Milky Way, and it contains somewhere between 100 billion and 400 billion stars, and every single one of those stars is, at some point in its life, a titanium factory. Not metaphorically, literally. In the nuclear furnaces at the cores of massive stars, where temperatures reach billions of degrees and pressures exceed anything achievable on Earth by many orders of magnitude, the process of nucleosynthesis builds elements from lighter ones. Helium fusing into carbon, carbon into oxygen, oxygen into heavier nuclei, And eventually, in the final catastrophic moments before a large star exhausts its fuel and collapses, the rapid capture of neutrons creates elements all the way up through the periodic table, including titanium, including the specific isotopes of titanium that make up the metal you can hold in your hand. When that star can no longer sustain fusion, it explodes, a supernova, an event so energetic that for a few weeks it can outshine the entire galaxy it belongs to. Hundreds of billions of stars, outshone by one dying sun. And in that explosion, all the elements that were forged in the stellar core are scattered outward at a significant fraction of the speed of light, seeding the surrounding interstellar medium with the raw material of future worlds. The titanium in your dental implant, the titanium dioxide in the paint on your wall, the titanium in the landing gear of the aircraft you last flew in. All of it was forged in a star that died before our solar system existed. The atoms were scattered across space in a supernova explosion that happened over 4.5 billion years ago, and over millions of years they drifted together under gravity, with hydrogen and helium and oxygen and iron and silicon and all the other elements, condensing first into a molecular cloud, then into a protostellar disk, and finally into our sun and the planets orbiting it, including the one you are standing on. The Earth itself is, in this sense, a recycling project, a vast, slow, gravitational gathering of stellar ash. And titanium, the ninth most abundant element in the Earth's crust by mass, was one of the ingredients that arrived in that original cloud of supernova debris, and has been here, locked into rock and sand and mineral grains for every moment of our planet's existence. Long before there were oceans, long before there was life, long before there was anything that could look up at the night sky and wonder what it was made of, the titanium was already here, waiting. Now zoom in. Come down from the galactic scale, past the solar system, past the Earth's orbit, through the atmosphere, down to the surface, all the way to a specific beach in Western Australia, on a morning when the low tide has pulled back to reveal a band of dark sand at the water's edge. That dark sand is ilmenite and rutile, titanium-bearing minerals deposited here over millions of years as rivers carried weathered rock from the interior of the continent to the coast, and waves and longshore currents sorted the heavy minerals from the light ones, concentrating them in exactly the kind of placer deposit that miners have been exploiting since the early 20th century. Pick up a handful of that wet, dark sand. You are holding in your palm the compressed history of a stellar explosion. The titanium atoms in that sand were forged at a temperature of several billion degrees in the core of a star that was dying when the Earth was not yet formed. They traveled across interstellar space for millions of years. They were incorporated into the forming planet 4.5 billion years ago. They were locked into rock. They were weathered out of that rock over geological time. They were carried by rivers to the sea. They were sorted by waves. And now they are in your hand, on a beach in the 21st century, and they weigh almost nothing, and they look, to the casual eye, like ordinary, dirty sand. This is what scale does to wonder. At the human scale, the scale of a morning walk on the beach, these grains are unremarkable. They are sand. They are the stuff you shake out of your shoes. But at the astronomical scale, the scale of stellar evolution and galactic chemistry, they are extraordinary. They are the remnants of a nuclear event so violent that it briefly outshone a galaxy. They are 4 billion-year-old travelers from the deep universe, come to rest on a beach in Western Australia, waiting to be scooped up by a dredge and turned into the white paint on a nursery wall. The philosopher Blaise Pascal wrote in the 17th century about the terror of being suspended between two infinities, the infinitely large and the infinitely small. He was writing about human existence, but he could have been writing about titanium because this element exists simultaneously at every scale. At the cosmic scale, it is common, a trace component of stellar nucleosynthesis, unremarkable in the chemistry of the universe. At the geological scale, it is abundant, 1% of the Earth's crust, woven through rock on every continent. At the human scale, it is useful, the metal of aircraft and surgeries and satellites. And at the atomic scale, it is extraordinary, a crystal lattice with a specific electronic structure that gives rise to all those macroscopic properties, the strength and the lightness and the corrosion resistance and the biological inertness, all of it ultimately traceable to the arrangement of 22 electrons around a nucleus of 22 protons. The number 22. That is titanium's atomic number. 22 protons in the nucleus, 22 electrons in the cloud around it. And in that specific arrangement, in the particular way those electrons fill their orbitals, in the specific energy levels they occupy, lies the explanation for everything. The corrosion resistance comes from the way the outermost electrons interact with oxygen to form that stable oxide layer. The strength comes from the way the crystal lattice distributes mechanical stress. The biocompatibility comes from the electronic inertness of the oxide surface. Every property, every use, every story in this entire history ultimately traces back to that number, 22. It is almost unreasonably small as the source of so much consequence. A jeweler in Tokyo is setting a titanium ring into a simple band. The ring is matte gray, lightweight, cool to the touch. The customer who commissioned it asked for something that would last, something that would not corrode, would not scratch easily, would be comfortable to wear every day for the rest of their life. The jeweler chose titanium without hesitation. To them, the choice is purely practical. But think for a moment about what that ring actually is. It is a small loop of refined metal, polished to a smooth finish, that began as beach sand on the other side of the world, that was processed through an industrial chain involving dredges and chemical reactors and inert gas systems and machining centers, that traces its existence back through 4.5 billion years to the nuclear furnace of a dying star. The customer will put it on their finger and wear it for decades, and it will never rust, never corrode, never react with their sweat or their skin. It will outlast them. It will outlast their children. If buried, it could survive, chemically unchanged, for millions of years. A ring. A piece of beach sand, transformed by human ingenuity and ancient stellar fire, worn as a symbol of permanence. Every titanium ring on every finger in the world is a piece of the universe, briefly shaped by human hands, carrying a history longer than life on Earth. That is not a metaphor. That is just chemistry and geology and astrophysics, speaking quietly through an object small enough to fit in your pocket. The global economy is built on assumptions. One of the most durable and least examined of those assumptions is that the materials needed to manufacture the things civilization depends on will be available, in sufficient quantity, at a manageable price when they are needed. This assumption is so deeply embedded in the logic of industrial planning that it is essentially invisible until it breaks. And the story of titanium in the 21st century is, in significant part, the story of what happens when it breaks. To understand the vulnerability, you need to understand the supply chain. And to understand the supply chain, you need to go back to Kroll. The process that Wilhelm Kroll developed in the late 1930s, the reaction of titanium tetrachloride with molten magnesium in a sealed, inert gas environment, is still, in the 21st century, the dominant industrial method for producing titanium metal, not a descendant of it, not an improved version of it. Essentially, the same process, scaled up enormously, but fundamentally unchanged in its chemistry and its constraints. This is remarkable, and not in a good way. In the 8 decades since Kroll perfected his method, semiconductor manufacturing has gone from vacuum tubes to chips with billions of transistors. Aviation has gone from propeller aircraft to spacecraft that land themselves. Medicine has gone from penicillin to gene therapy. And titanium is still made the same way it was made, in a small American government laboratory in 1938. The Kroll process works. That is the problem. It is good enough, reliable enough, and established enough that the enormous capital investment required to develop and commercialize an alternative has never quite been justified. Every decade or so, a research team announces a promising new electrochemical method for producing titanium directly from oxide. Cheaper, less energy-intensive, continuous rather than batch-based. And every decade or so, the announcement quietly fades as the engineering challenges of scaling up prove more difficult than the laboratory results suggested. The Kroll process sits in the center of the titanium economy like a very old, very reliable machine, that everyone knows should be replaced, and nobody has gotten around to replacing because it keeps working, and the replacement cost is enormous, and the timing never quite seems right. And around that central machine, the supply chain has organized itself in ways that create extraordinary concentrations of risk. The production of titanium sponge, the raw, porous metal that comes out of the Kroll process before it is melted and alloyed, is concentrated in a very small number of countries. Japan, Russia, Kazakhstan, China, and Ukraine account for the overwhelming majority of global production. The United States, despite being the country that developed the Kroll process and the country with the world's largest aerospace industry, and therefore the world's largest appetite for titanium, produces only a small fraction of its own titanium sponge. It has chosen over the decades to import most of what it needs because imports were cheaper and the supply seemed reliable. This worked more or less for decades, and then the world changed. The disruption of Ukrainian titanium production, which had been a significant contributor to global supply, particularly through the mining and processing operations in the country's mineral-rich regions, sent shockwaves through the aerospace industry in ways that the public largely did not notice, because the full effects took time to work through the system. Aircraft are not made quickly. The gap between a disruption in raw material supply and a disruption in finished aircraft delivery can be measured in years. But the aerospace companies noticed immediately. Boeing and Airbus both moved quickly to reduce their dependence on specific sources, qualifying new suppliers, drawing down strategic stockpiles, redesigning some components to use alternative alloys. The scramble was expensive and disruptive and illuminating. Illuminating because it revealed, with uncomfortable clarity, exactly how little redundancy had been built into a supply chain for a material that both companies described as critical and irreplaceable. Consider what that word means in practice. Critical. When engineers use it about a material, they mean that there is no substitute that performs equivalently in the relevant application. For titanium in jet engine compressor blades, the statement is essentially true. The compressor section of a modern jet engine operates at temperatures and stresses that eliminate most alternative materials on either weight or thermal grounds. Aluminum cannot handle the heat. Steel is too heavy. Nickel superalloys are heavier and more expensive. Titanium, in specific alloys, is the right combination of low density, high strength, and thermal stability. There is no drop-in replacement. You cannot redesign a jet engine compressor around a different material in the span of a supply disruption. You cannot even redesign it in 5 years. The tooling, the certification, the testing, the regulatory approval, the timeline for a material substitution in a certified aircraft engine is measured in decades. Which means that when the titanium supply chain is disrupted, the aerospace industry does not pivot. It waits. It pays whatever it has to pay. It draws down stockpiles, it manages production schedules, and it hopes the disruption is temporary. The same logic applies, in varying degrees, to naval construction, medical device manufacturing, semiconductor fabrication equipment, and a dozen other industries where titanium has become structurally embedded over the past 70 years. Each of those industries chose titanium for good reasons. The right combination of properties for the application, available at a manageable price from what appeared to be reliable sources. None of them at the time of adoption was thinking about what the supply chain looked like 3 or 4 levels upstream. None of them was modeling the scenario where the countries that produced the sponge became unavailable simultaneously. The vulnerability is not a secret. The United States government has, at various points, classified titanium as a critical mineral, a designation that acknowledges the combination of strategic importance and supply risk. The European Union has done the same. Various task forces and reports and policy documents have been produced over the years, recommending diversification, domestic production investment, strategic stockpile maintenance. Some of these recommendations have been partially implemented. None of them has fundamentally changed the structure of the supply chain, because changing that structure requires sustained investment in politically unglamorous industrial infrastructure, in smelters and chemical plants and mining operations, at a time when political attention tends to flow toward more visible technologies. The result is a world in which the material that holds aircraft together, that reconstructs shattered bones, that makes spacecraft survive re-entry, and that keeps the walls of your home white, is produced at the critical choke point of the Kroll process by a handful of facilities in a handful of countries, some of which are geopolitically stable, and some of which, demonstrably, are not. The Titans, in Klaproth's mythology, were imprisoned by the gods in the pit beneath the earth. In the 21st century, titanium is imprisoned by a different kind of constraint, not geological, but economic and political. The metal that took 150 years to free from the rock is, in its industrial form, still not entirely free. It is held instead by the concentrated geography of a supply chain that the world built for efficiency and is now discovering was built for fragility. And the question of how to change that, how to build resilience into a system that is optimized relentlessly for cost, is one of the defining industrial policy challenges of the century we're living in. The stakes are higher than they appear from the outside, much higher. And the next chapter will show you exactly how high, by asking you to imagine, just for a moment, a world where the supply does not just slow down, but stops entirely. Imagine it is an ordinary Tuesday morning. The city around you is doing what cities do, moving, humming, consuming. Coffee is being brewed, meetings are starting, planes are being loaded at the airport, surgeries are being scheduled at the hospital across town. It is indistinguishable from any other Tuesday, except for one thing. Sometime during the night, in this thought experiment, in this controlled hypothetical that I am asking you to hold in your mind for the next few minutes, every object, every component, every compound that contains titanium has simply ceased to exist. Not broken, not degraded, vanished, as if the element had been retroactively removed from the periodic table. Let us be precise about what happens next, because the precision is the point. The aircraft sitting on the runway at the airport does not fall apart dramatically. It just becomes unflyable. The compressor blades in its engines, the structural fasteners in its fuselage, the hydraulic system components, the landing gear, gone. The aircraft is a shell. Every commercial aircraft in the world is simultaneously a shell on the same Tuesday morning. The global aviation network, which moves roughly 4.5 million passengers every day and carries time-sensitive freight that underpins pharmaceutical distribution, fresh food logistics, and electronic supply chains, stops. Not slows, stops. At the hospital, the surgical ward faces a different kind of crisis, quieter and more personal. The titanium instruments, the forceps, the retractors, the cutting guides are gone. But worse, every implant that was scheduled for today's surgeries does not exist. The hip replacement that was going to give a 73-year-old man his mobility back. The spinal fusion that was going to relieve a woman who has not slept without pain in 3 years. The dental implants, the bone screws, the cardiac stents being held in sterile packets in the supply room. All of it gone. And it is not just what was scheduled for today. Every titanium implant already inside a living human body is also gone, which means, in this thought experiment, that the 500 million people worldwide who have titanium dental implants suddenly have gaps in their jaws. The patients with titanium hip replacements have femoral heads that are no longer supported. The people with titanium spinal hardware have vertebrae that are not fused. This is the point in the thought experiment where the scale becomes genuinely overwhelming, and it is worth sitting with that feeling for a moment, because the feeling is the point. The feeling is the accurate response to accurate information about how deeply this element has woven itself into the infrastructure of modern life. Continue. The paint on the walls fades. Not suddenly, but think of every surface that has been coated in titanium dioxide-based white paint. Every painted interior wall in every building in the developed world loses its brilliant whiteness and becomes the dull, off-white or gray of uncoated substrate. The psychological effect of this, distributed across billions of living spaces, is not trivial. White is the color of cleanliness, of space, of modernity. Its absence registers as a kind of dimming. The sunscreen in the bathroom cabinet, the toothpaste by the sink, the white candy coating on the pill you take every morning, all of them lose their opacity, their consistency, their function. The paper in books and printers is no longer bright white. The road markings that guide traffic are gone. The world, without titanium, is a noticeably grayer, dimmer, more precarious place. And the people in it are, simultaneously, losing access to aircraft, losing surgical care, losing the industrial infrastructure that the absence of a single element has revealed was far more load-bearing than anyone understood. This is fiction, of course. The thought experiment is a device, not a prediction. But the device works because the underlying facts are real. The dependencies are real. The concentration of the supply chain is real. And the question the thought experiment is designed to make you ask, what actually happens if the supply seriously degrades? Not vanishes overnight, but degrades over years, which is a scenario that is not fictional at all. That question has no comfortable answer. The real answer is that the aerospace industry consolidates around whoever controls supply. Aircraft get more expensive and scarcer. The medical device industry finds partial substitutes for some applications and lives with degraded performance in others. The paint industry reformulates at enormous cost, seeking alternatives that are almost as good, but not quite. Geopolitical leverage shifts toward the countries that produce titanium sponge. The world does not end. It adjusts. But the adjustment is painful, expensive, inequitable, and slow. So what is actually being done about this? Here is where the story pivots from threat to something that feels, carefully, like possibility. The next 50 years of titanium are being written right now, in laboratories and startup offices and government research centers, and the directions being explored are genuinely extraordinary. Three-dimensional printing, additive manufacturing in the technical vocabulary, is transforming how titanium is used in aerospace and medicine. Traditional titanium manufacturing is extremely wasteful. A machined aircraft component might begin as a block of titanium that is 90% removed by cutting, producing enormous quantities of expensive scrap. Additive manufacturing builds the component directly from titanium powder, layer by layer, depositing material only where it is needed. The buy-to-fly ratio, the mass of raw material purchased versus the mass of finished part, drops from 10 to 1, or worse, towards something approaching 1 to 1. Less material, less waste, lower cost. And the geometries achievable with additive manufacturing are impossible with conventional machining. Internal cooling channels, lattice structures, organic shapes that optimize strength while minimizing mass. The same technology is entering medicine in ways that make Brånemark's original osseointegration discovery look like a starting point rather than an endpoint. Custom titanium implants, printed to match the exact geometry of an individual patient's bone, are already in use for complex reconstructive surgeries, cases where the damage or deformity is too irregular for a standard, off-the-shelf implant. Researchers are printing titanium scaffolds seeded with the patient's own bone cells, creating implants that are not just tolerated by the body, but actively remodeled by it, gradually incorporating the patient's own tissue into the implant structure until the boundary between metal and bone becomes genuinely biological rather than mechanical. And at the far edge of the possible, engineers designing structures for the era of sustained space exploration are looking at titanium, specifically titanium alloys hardened against radiation damage, as the structural material for habitats, for propulsion components, for the frameworks of space elevators, for the pressure vessels of nuclear reactors in deep space propulsion systems. The material that was forged in a dying star is being considered for the machines that will carry humans out toward other stars. That is a sentence worth pausing on. But every one of these futures runs through the same bottleneck, the Kroll process. The magnesium reduction, the batch reactors, the sealed retorts, the inert gas systems. Every kilogram of titanium metal in every printed medical implant, every additively manufactured aircraft bracket, every proposed space habitat component, it still has to come first from a Kroll reactor. Until that changes, the future of titanium is constrained by a process invented by a solitary man in a government laboratory during the Great Depression. The most promising alternative, direct electrochemical reduction of titanium dioxide, Developed in variants by research teams in Cambridge, in Australia, in Japan, in China, has been demonstrating laboratory-scale feasibility for over 2 decades. The physics work, the chemistry works, the engineering of a reliable, continuous, industrial-scale electrolytic titanium reactor has, so far, not quite worked, in the sense of producing metal at a cost that competes with the Kroll process in the real market. But the gap is narrowing. The energy economics are shifting as electricity from renewable sources becomes cheaper. The pressure from supply chain vulnerability is intensifying. The investment is beginning to flow. Perhaps, in the next 20 years, the curse will finally be broken at the industrial level, the last chain holding the Titan underground severed not by chemistry alone, but by the combination of necessity, ingenuity, and the particular human stubbornness that has been pursuing this element since a curious English pastor knelt by a riverbank in 1791. Or perhaps not. Perhaps Kroll's reactor will still be running, in essentially its current form, in 2075, producing the sponge for aircraft and implants and paints and spacecraft, reliable and irreplaceable and frustratingly unchanged. That uncertainty, that genuine openness of the future, is the last thing the mythology suggests. The Titans were imprisoned. They did not stay imprisoned forever. The question was never whether they would escape. The question was always when, and at what cost, and what the world would look like on the day they did. Go back to Cornwall, one last time. It is autumn, and the light is doing what autumn light does in the English southwest, arriving at a low angle, turning the water bronze and the wet sand almost gold, making ordinary things look briefly mythological. A person is walking along the bank of the Helford River. They are not William Gregor. Gregor has been gone for more than 2 centuries, but they are walking the same ground he walked, and the black sand is still there at the water's edge. The same heavy, dark grains, the same faint magnetic pull if you hold a magnet near your palm. The same element, unchanged by the centuries, unchanged by everything that happened after. The black sand does not know that it was found here, does not know that its discovery set in motion one of the strangest and most consequential stories in the history of human materials. It does not know about Klaproth's library in Berlin, or Kroll's sealed retorts in a government basement, or the stratospheric speed of a reconnaissance aircraft whose airframe burned copper-colored at the edges of the atmosphere. It does not know about the Swedish surgeon who could not remove his optical chamber from a rabbit's bone, or the 8 million tons of white pigment that flow through the global economy every year, or the question of whether a new electrolytic process will finally replace a method invented during the Great Depression. The sand simply sits at the edge of the water, as it has for millions of years, and waits. This is what titanium has always done, waited. It waited in the cores of dying stars for the explosion that would scatter it across space. It waited in the molecular cloud for gravity to pull it together into a world. It waited in the rock for weathering to free it to the rivers, and in the rivers for the currents to carry it to the sea, and at the sea for the waves to sort it into those dense black layers at the tide line. It waited in Gregor's vials, and in the pages of journals nobody read, and in the laboratory failures of 100 chemists who got close, but not close enough. It waited in Kroll's retorts while the magnesium stripped away the chlorine and the argon held back the air. It waited in the aerospace procurement systems while engineers slowly understood what it could do. It waited inside human bodies for the bone cells to find their way to its surface and begin to build. Patience is the quality the mythology forgot to give the Titans. The ancient Greeks imagined them as creatures of violent, impetuous force, beings who could not wait, who struck before they were ready, who were defeated in part because they lacked the long view. Their namesake element is the opposite. Titanium is the most patient material in the world. It has been here for 4.5 billion years. It survived every geological catastrophe the Earth has ever produced. It survived every human attempt to destroy its integrity with contamination and haste. It can wait another 50 years for a better extraction process. It can wait another century for humanity to figure out what to do with it in deep space. It is not going anywhere. It is in the sand under your feet, and it will be there after you are gone, and it will be there after everyone reading or listening to this story is gone. Quiet and dark and heavy and patient, carrying the light of a dead star inside every grain. There is a particular kind of wonder that comes not from the exotic and the distant, but from the familiar and the overlooked. From the realization that the ordinary world is, on close examination, made of extraordinary things. The paint on your wall, the filling in your tooth, the fuselage of the plane that took you somewhere important, the white page this story might have been printed on. None of these things seem remarkable until you follow the chain of events that produced them, all the way back through the industrial chemistry and the Cold War engineering and the failed experiments and the solitary obsessions and the stellar nucleosynthesis, and then look at them again with that knowledge sitting behind your eyes. They are still ordinary. They are still the furniture of daily life, too familiar to notice. But they are also, without contradiction, ancient and cosmic and hard-won and improbable. They are the products of a 4-billion-year journey from a stellar explosion to a corner of a room where someone is going about their day without thinking about any of this. That gap between what things are and what we know about them is where wonder lives. And titanium, more than almost any other material, rewards the effort of crossing that gap. Because when you cross it, what you find on the other side is not just a metal. You find a story about human stubbornness in the face of impossible problems. You find a story about the accidental beauty of scientific discovery. You find a story about how the same properties that make something useful in one context, the oxide layer, the inertness, the patience, make it miraculous in another. You find a story that begins with a pastor in muddy boots on a riverbank in 1791 and ends, for now, with a question about the future that nobody can yet answer. And you find, underneath all of it, the oldest story of all. The one where something enormous and powerful and ancient is locked inside something small and ordinary, waiting for the moment when someone curious enough, stubborn enough, patient enough, finally reaches down and picks it up. The black sand is still there at the edge of the Helford River. The tide comes in, the tide goes out. The titanium waits.